Well, good morning everybody. As promised, I'm putting this video out on how to use the finite element method. I appreciate your understanding for me leaving a little early yesterday. I gotta say that the ceremony there for the soccer team was one of my most rewarding nights as a parent. My son was one of the captains of his high school team. He's a senior on the varsity soccer team there at State High. They won their what's it called, their division or whatever it is here within the state. And so last night, Kevin had to give a speech, which he did an excellent job, and he thanked the parents for all they had done and talked about his last day, the last game standing on the field, thinking that basically that's it for his soccer career, at least in terms of formal career of playing soccer. And then they had an award ceremony, and Kevin won basically the biggest award they gave to the team for his leadership. And finally, the coach had some comments at the end and saved Kevin for last. And he has two small boys and said he hopes that they grow up to be like Kevin. So, as a parent, it's kind of like winning the Super Bowl, basically. Anyway, so let's get started with these examples of using the finite element method. The first one is a pin string, so it's exactly what you think the pin string should be. It's the second order system that has pinned at either end, and this is the code that actually put it together. So at the top of the code there you have basically, in this case we're actually going to plot the natural frequencies versus the order or number of elements for the finite element method. So that's the plot you can see over here that this code produces. So in this case we wanted to run from a minimum value of 5 elements to a maximum of 30, and hence this is why you go from 5 here to 30 in your plot. And then it's just a standard, just kind of let all the parameters be equal to 1, and you initialize a vector that's going to be storing all these eigenvalues. Okay, so we're at this loop right here, and again we're just looping through, and each time through the loop we have to make our big M and K matrices. So the M and K are those global matrices that we were talking about that are going to be sort of, in this case, scale of n plus 1 by n plus 1. And so what you're going to find is initially we're going to make these matrices kind of the full size, which would be an n plus 1 by n plus 1. But later on, because of the pin boundary conditions, we're going to remove the first and last rows and columns from those matrices because we have the pin boundary conditions. So as I mentioned, the assembly is very simple. You're basically, if you look at the big M matrix here, you're just going down the kind of diagonal and putting in these, in the case of the M matrix, putting in these little MI matrices. And these are the matrices that you remember seeing from the notes. They've got the mass unit length out here. They have the length of the, well, basically L over N is like the length of each element over here. And same for K. K has that form we had in the notes. And so basically once you initialize them to 0 up here, you basically add in, for each of these 2 by 2 little blocks, you just add it in. So as you kind of march through these elements, you just add in each of those little submatrices to create the overall matrix. And then here we have removing the first and last rows and columns. And then this is the eigenvalue problem here. So just take the eigenvalues of M over K. Now, in this case, we're just looking at storing the eigenvalues d there. But if you want to plot the actual mode shapes, then you have to actually have both eigenvalues and the eigenvectors. I don't remember if there's any. Oh yeah, there are some mode shapes here. So we don't save the modes for every n, just the last one. Plot up the last result. Okay, so this is just storing, and remember the eigenvalues are the frequency squared, so don't forget about the square root in there to get your natural frequencies, omega n. Alright, so once we have gone through this exercise of getting the whole vector of natural frequencies there, we can plot them up. And you know, they're sorted, so the sorting just basically goes from the lowest frequency to highest. So we'll take the first, the second, second, third, fourth, and fifth natural frequency. So you should see up here on your plot, you know, basically we're looking at 1, 2, 3, 4 natural frequencies. Second, third, fourth, and fifth. 4 natural frequencies. Okay. So those are just being plotted up versus order, and kind of the usual thing here. Now, for some reason, I did plot some lines here. At pi, this is basically this would be omega 1, the first natural frequency we know from the theoretical. 2 pi is omega 2. And for some reason it didn't show up here. There should be lines. Over here. So there should be a blue line that kind of goes over here at pi. This is omega 1. There should be a red line. I'm not sure why they didn't show up here. Omega 2. But you can see that these basically are converging from above. 3 pi is somewhere in here. Are converging from above. So you can see that they're coming down and approaching the actual value. So, you know, for example, if you needed to get your first natural frequency and mode shape good to say, you know, just for the first mode, you might pick, you know, n equal 10. So, you know, if you're just interested in getting an accurate number for, you know, maybe this would be n for your first mode, whereas if you're looking at getting the fourth mode in this case, this black line here, you know, you might go up here to say 20. Something like that. And sorry for it's so stuttery there when I change size. Okay. Alright, so then we want to plot the mode shapes out. So plotting the mode shapes, of course, you have to have an x vector. And it's just going to be the x values for all of the elements. So you have the first element is 0, the last element is L. Now remember, we took out the first and last rows and columns, so what you have to do is when you plot the actual mode shape, this, let's use red here. This is x equals 0, and this is x equal L. So you have to manually put in, when you plot the overall shape, you have to put in the two values at x equals 0 and L, because we didn't solve for those, so those are not part of the eigenvector. And this is just to scale, you know, just to scale it so the eigenvalue maximum value is equal to 1. Okay, and because this is the last time through the loop, this is actually the case that we had for the maximum n. That's what we got for our mode shapes for the maximum value of n. And I just had, you know, down here, this sprintf thing is just printing the natural frequencies that you have. So again, it should be, this is in hertz, so half a hertz, 1 hertz, 1.5 hertz, 2 hertz are the theoretical values for the natural frequencies. And clearly these mode shapes look pretty reasonable, right? The first one is this one here, just one kind of loop, and then you have the second one. So this would be like W1, this would be like W2, and that kind of thing. Okay, so it certainly look like reasonable mode shapes for a string. But you can see, you know, you can see if you zoom in down here, you can see this is linear interpolation. And that's just the default when, of course, when MATLAB plots things up, it draws a straight line between the points. So you don't have to do anything special to get linear interpolation. But that's actually correct in the sense that, you know, these elements are linear elements. All right, so that's the pin string. Now, I wanted to show you the kind of gantry crane model here. And I'll post this, maybe I'll stick it on the end of that last, no, I guess I'll combine all these together and post these as a PDF. So this is a gantry crane. So in this case, there's a massive part on top, M, and there's a small mass, M, on the other end. And then you have a cable connecting those two of mass per unit length rho, and tension that varies along the length. And we're looking to solve for the overall displacement W of x and t as a function of x, which goes from 0 to L along the length of the cable, and t, which is time. And of course G is what's acting down in this case to tension the cable. So what we're going to do with this problem is you just start with the free string matrices, and those are the ones where we just started out initially without taking out the last and first rows and columns. We're going to add the capital M to the first element of the mass matrix, and that's because if you think about it, really this finite element thing is you can have a distribution of mass as a function of x. In this problem, there's like a delta function at x equals 0 and a delta function at x equal L. At x equals 0, there's additional mass capital M. At x equal L, there's the additional mass small m. And the other thing we have to do from the pin string case is we have to make p a function of x. So we have to use this expression for p of x. All right, so let's go back to MATLAB and the gantry crane finite element code here. Okay. So with the gantry crane code, it looks very similar up front. We need to have a few more parameters in there. We're again going to plot the eigenvalues versus the order, the number of elements. The numbers now are more representative of an actual gantry crane, so it's a 10-meter long cable, a mass of 2 kilograms on one end. Mass per unit length is 2 kilograms. The mass of the gantry, capital M, and again you have to be careful because we have another capital M later on, so I don't want to use that, so it's mg is the variable, is 50 kilograms, and the mass of the payload is 10 kilograms. So these units are all, metric. And so then we go through the same loop we went through before. from n equal n min to n max. We initialize the matrices to zeros, define mi and ki. And what's interesting here is rho is constant, so that you don't have to change as you go down the length, but p is not. So now we actually have pi inside the loop that's basically cutting and pasting these mass matrix and k matrix, the element matrices in. Now this one depends on pi. And here's the equation for p of x. So you actually have to put it inside the loop that's generating these element matrices. Okay, but otherwise this code looks exactly the same as a pin string, and instead of down here, instead of eliminating the first and last rows, we just add in the mass of the gantry to the 1,1 term and the mass of the payload to the last term. And then same procedure to get the eigenvalues and eigenvectors, and then we plot those up. In this case I don't really have a theoretical value to compare them with, but since we sort of checked out our code with a pin string, we're fairly confident that these numbers are going to be reasonable. And again, you see the eigenvalues converging from above. This system does have a zero eigenvalue because the whole thing can translate and continue translating, so that's why we have this kind of blue curve down here. Blue set of first eigenvalues are 0. And if you look at the mode shapes, they're actually also very reasonable. The first the first mode actually I think is straight line. I don't know if you can, the 0 mode, can't really see it on here, but there should be one mode which is basically just a straight line. Constant amplitude of 1, maybe it's up there, you just can't see it. And then you have, the second mode here, 2, so this is the first mode, that's the second, this would be the third, and that would be the fourth. So a typical thing, as you get increasing frequency, there's more sort of curvature to that mode. So here we have our natural frequencies going from 0, 0.2, 0.56 to 1. And so what's interesting in this case is that, typically people neglect the vibration modes of the cable. And, in this problem that's really not a good idea, because the swing mode, the square root of g over L, which is basically this one, something like the square root of g over L sort of mode that looks pretty much like a rigid, rigid kind of swinging pendulum, is actually very close to it's only, half of the first kind of real, vibration mode that has some curvature to it. So depending on what you're doing with this crane, that could be a significant vibration in that second mode. So, by describing the mode shapes, I'm basically doing the same thing we did before by looking at the eigenvectors and plotting them up. In this case, you don't need to worry about adding zeros to the 2n because we're solving for all of the nodes in this problem. Just plotting out here the frequencies that you get. And then we want to actually solve for the response. So we want to convert this over into a state space form, because that's what we do when we want to do a simulation. And we're going to put a force in to the gantry and then look at the response of the payload. So we could look at the response of the whole cable, the whole system if we want, but in this case, let's say the input here is, let me see if this is a little better maybe. I don't know if this is a better way for you to see it on the screen or not, but it's a little easier to write. So in this case, blue, input force at x equal to 0. So that means that you basically have an input vector, which is the same length as your kind of your mass matrix or your Q vector, and we only have one element which is non-zero, which is the first element. So the first element is non-zero. Okay, so the rest of the formulation is pretty much standard, with one exception. I think there should be an M inverse on F. Not sure how that's going to affect things, but there should be an M here. I made the mistake on another one and I fixed it, but not this one. So when you write your equation, of course, it's like M Q double dot plus K Q equal to this F vector. And then when you write this in terms of a first order equation, of course your first one is Q dot is equal to, V, your X vector has two parts, one is V and one is X. Q double dot is equal to minus M slash K Q plus M slash F times which your input here, which in our case is going to be, say, F of t, whatever that is. So there should be an M inverse, so that would probably change the response. Alright, so in our output here, the output comes from y equals cx plus d, kind of that standard equation there. So in this case, y is equal to c of n plus 1. C of n plus 1. C of n plus 1. Yeah. That's going to be W of L and T, which is basically the last element. If you look at your X vector for the state variable form, X is equal to Q, and Q dot. So the Q vector is n plus 1 length long, right? Those are all the nodal displacements. So if you take the last element of Q, which would be the n plus first element of Q, that is the displacement at the tip. So that's why we're having our C matrix have that form. Okay, so basically we want to run a simulation, and it's kind of neat that with these kind of systems you can actually do what's called input shaping, where you can give a certain input to the gantry, and of course the objective is to move the payload from, say, position 0 to, say, some other position, but you'd like it to arrive there with as little vibration as possible. And so this input here is just, if you look at this F input is just basically a square pulse, looks like this, where this area here is the same as that area. So we'd expect that you basically hit it with a pulse to get it going. It's swinging, it's translating and swinging, and then you hit it with a second pulse to decelerate it and stop. And so this is the output result from LSIM, and you can see basically here's the first pulse and the second pulse. So this is input F of t that we're putting in, and you can see the vibration response here is basically W of LT. So once you give the initial pulse as you expect, you're sort of translating and swinging the payload, and then when you give it the second pulse, it sort of stops. And there's some, I didn't figure this out, but there is some combination of pulses that once you're done translating, there actually will be no residual vibration. And we actually published a paper on that for these kind of distributed systems. So that's the gantry crane, showing how you can use it to calculate natural frequencies, mode shapes, and time response. Okay, let's look at some beam examples next. So if we go back here to our list of examples here, this is the next two ones that we're going to look at. Maybe I'll just describe both of them and then we'll go forward and just look at the MATLAB code without coming back to this. So there's two problems we're going to look at. The free beam, so that's FFbeam, FEM.M, and there's this nodal beam isolation system. So I think everybody knows what the free beam looks like. It's just a beam with no boundary conditions. It's the simplest finite element model to put together because all you do is you just put all the element matrices together into one big global matrix. You don't have to worry about eliminating any rows or any columns. And nodal beam isolation is actually the same. The only difference is that the boundary conditions are the same, right? You have no shear and no moment on the ends. But now we're actually anchoring this beam to the ground with a support. Now, one of the disadvantages of, driving your equation using Hamilton's principle is it's very hard to get the reaction forces. Newton's method, of course, automatically gives you the reaction forces, and you could probably draw some free body diagram and look at the shear and figure out what the actual reaction forces are if it was just rigidly connected at these 2 points, xk and L minus xk. But by putting springs in there, you can actually have an output, which is the reaction force. And the reaction force is just k times the displacement, W, at xkt. And so we have these two springs on either end. We're forcing it in the middle. And we like to see if we can't generate some sort of node so that you're exciting the system at a certain frequency and there's basically no force being transmitted to the base. And as I said, these are actually used in helicopters to isolate the rotor from the fuselage. So it's very easy to implement this actually in finite elements. All you have to do is add k, these stiffnesses k, to the right places in your to the right finite elements basically. Now, of course, the finite elements have finite width, so it's not a perfect approximation. We'll see the results aren't exactly perfect, but in terms of implementation, it's pretty simple. So for the helicopter application, you're trying to minimize the reaction forces at n per rev. So if you have 4 blades, typically you're getting 4 per rev beating on the fuselage, which can be very annoying for the people riding in it. All right, so let's go look at how we do these two examples in MATLAB. We'll start with the free beam finite element, and so I think with this problem, I don't know, we're kind of looking at convergence to a certain extent. We're going to look at these 4 different number of nodes and see what the eigenvalues look like, but we're not going to actually plot eigenvalues versus order. Okay, so we have a certain length. It's a pretty long beam. It's not a helicopter application, 10 meters long. Certain mass per unit length and bending stiffness. And so we can get some theoretical eigenvalues from our book. Meyerowitz says that for a free beam, the first 2 natural frequencies should be 0. The third is basically 12.6 hertz, and the fourth is 35 hertz or so. You remember our element matrices, Mi and Ki, that we derived in the notes? And we're looking at changing the number of nodes. So we're starting out with a minimum value of 3 nodes, which would be 3 elements, I'm sorry. So in that case, you're going to have 1, 2, 3, 4, 5, 6, 7, basically degrees of freedom, because each one of them has 2. So you basically end up with an M matrix that's 2n plus 2 in terms of dimensions. M and K are both that size. And you basically do the same thing we did before. You're basically start out, initialize those matrices to 0, and then go through and insert basically these MI matrices times rho Li, in this case it's EI over Li cubed. So this example is just assuming everything's uniform for simplicity. Okay, so then it's the same deal. You look at calculating the eigenvalues and eigenvectors, and you can plot up the actual shapes. Now this stuff here, this kind of analysis here is basically, you'll recognize these are the actual interpolation functions, right, that you're using. So if you have just a few nodes, you can get a better idea of what the shape looks like of that mode by using interpolation. If you have enough nodes, then you don't even worry about interpolation, just draw straight lines between it like regular plotting. But I wanted to show you how you could actually do interpolation. We're basically, we're running through, and let's see, where's our loop ending? I nodes. Okay. Each time we run through this big loop here, picking a different number for n, we're going to calculate and plot just the third and fourth modes, because the first and second modes are going to be, these 0 eigenvalues, and they're hard to get. They're repeated, so you can't just use a standard sort of eigenvector analysis. You get crazy stuff. So we're just going to plot third and fourth, and we're going to use this interpolation here that I talked about. And so this little loop in here is basically doing the interpolation. You really don't have to do that. You'll see in the next example I don't do that, but it's kind of cool looking in the end. And then you plot the actual nodes, and the nodes are the W's, and you plot the whole functions just to show how they look. And here are the results. So if you look at the first case where we had 8 nodes, 1, 2, 3, 4, 5, 6, 7, 8. So the little circles are each of the nodes. And remember, at each node we have both a solution for the displacement and the slope. So you can see that between nodes you actually get a curved line, and that's the interpolation. If you just use linear interpolation, of course you just would have got something straight across. So the interpolation here gives you a curve. And you can see, first of all, if you look at this for the third and fourth mode, remember the first is going to be kind of straight, second is going to be the slanted line. Those are the 2 rigid body modes. And these are supposed to be symmetric, right? I mean, it's a symmetric problem, free beam, and yet you can see this displacement and that displacement are not the same. So they're not really converging very well. So as you move over to say the case where you have 16 nodes in this case, you can see things are getting a little better. They're starting to look more recognizable. Again, these are the natural frequencies, 2 zeros, and then 11 and 30, and I think they were supposed to be like 12 and a half and 35 or something like that. So eventually, if you go down here to 64 nodes, you can see you don't really need to interpolate here. There's not much in terms of interpolation. Also, some of these guys look a little funky interpolation things here. I guess that's, I don't know if you zoom in there. But you pretty much just plot, in this case, the node points, and you get a good idea what the shape is. And you can see now that, this is going -1, this is +1. This mode shape is showing a nice symmetric shape to it. So we're sort of converging, and these numbers are getting close to the theoretical values for a free beam. One thing I haven't really figured out is that you're supposed to get convergence from above, and yet you'll notice this is going from 9.6 to 11, so it's actually converging from below. I have a feeling because this problem has the zero eigenvalues, it kind of screws up that convergence property, but haven't quite figured it out. I think it looks reasonable though. Okay, so that's how you do beam type problems. And let's look at the last example, which is this nodal beam example. And oops. Nodal beam, FEM, here we go. Okay. So, this is the nodal beam. And again, the only difference, if you look at this code, is that we have to place these support springs on the beam. So this part right here is basically finding where the springs are located, you know, based on some x, so you give it some x value. And if you look up here, there are two cases that I did. One was with springs at the ends. The other one is kind of moving them inward to some position. In this case, x equal 2. The length is, total length is 10. So I've got the results for both of those down here. So this is basically putting the springs on the beam. And again, because there's only a certain number of nodes, you can't put them exactly where you want them. But in this case, I'm just using n equal 2 to the 8. So whatever that comes out to be in terms of number of nodes. And I played around with that number, you know, to see what gave me the best results, and this seems pretty reasonable. So everything else is the same. You'll notice here I didn't do any interpolation, so I'm just plotting the node points here, and the frequencies that come out of it. Now, of course, we're interested in whether the system has a zero, so to speak. Can we introduce a zero in the system such that when you're forcing it at a certain frequency, there's no transmitted force to the base? So we have to make a state space system from that. And you'll notice here I did put the M inverse, which is supposed to be there, so it wasn't there in that previous example. Now in this case, we're actually trying to put a force near the center of the beam. Here's your input force. And you have to be careful because remember with this formulation that the odd elements of Q are displacement and the even ones are rotation. So if you're going to put in a force, it has to appear in the displacement equation. And so in this case, n plus 1 is going to be an odd number, and that's basically the location closest to the middle. The total length of the vector is 2n plus 2, so half of that is going to be n plus 1. Okay, so we just formed the state matrices, same as before. The only thing different here is that we're going to put in this spring, the output here, you know, input equals force at x equal basically L over 2, and our output here is equal to the force, or what's called reaction force. Which is going to be this Ks W of L, I guess this X K comma T. Okay, so that's what's giving that C and D matrices. And once you have a state space system, you can do a Bode plot, and you get the results shown, I guess, on the next page. So there's two cases I ran. One was with the spring at the ends. So in that case, you basically should have a symmetric system, so you can see Remember the free beam had like these rigid modes? Well, now blue is the first mode. So here's your W1. Red is the second mode if you look at the color scheme there. So this is W2. And green is the third mode, so this is your W3. And black is your fourth mode. So this is W4. And here are the natural frequencies that you get for these in radians per second. So these modes look pretty reasonable. They should be symmetric. So you can see, for example, W2 is going from -1 to +1. And that makes sense. You have kind of this rocking mode where the whole beam is kind of rocking back and forth, sort of like a rigid body. Omega 1 is the whole beam is bouncing up and down. You can see the springs are having some impact because it's not a straight line anymore. The beam is curving. And then this is actually the mode here, W3, that we're interested in exciting the system near W3, because that actually has node points. So if you look, this mode actually goes through 0 at 2 points here and here. So you'd expect that if I put a spring right here and right here, and I excited the system such that that mode is vibrating, you really shouldn't see any forces being transmitted because the mode doesn't have any displacement there. If there's no displacement, there should be no force. So this is the case with the spring at the ends. It looks reasonable. You can plot a frequency response. It looks like this. Now, remember the output is going to be the spring force at the end. So you see all of the natural frequencies appearing. Although, yeah, some of these are a little, let's see, what were the numbers? It was 1427. So 14 is, this is your 14. So if you look here, this is omega 1. Omega 1. And this is actually omega 2. Now why, you may ask, is omega 2 almost look like it's perfectly canceled? Well, remember our input to the system was a force at x equal L over 2. So our force actually was coming in right here. That's where f of t is being applied. And you'll notice that the second mode has 0 displacement at that location. So what that means is even if you can't excite that mode with a force at the center. Now the reason we see like a sort of a peak, it's almost a perfect pole zero cancellation, but not quite. Why is it not perfect? Is because the theory says there should be nothing there. So it should be a perfect cancellation. But finite elements, you can't get that exactly in the middle, and there's some spillover effect of the discretization, and so therefore you see a little thing like that. Now, omega 3 comes through loud and clear because it has it can be forced and sensed at the boundary. But here's omega 4. Again, it looks like it's kind of canceled out, and that's because, there's sort of this pole zero cancellation because W4 also goes through 0 at the center of that beam. Okay, so everything looks very reasonable from the viewpoint of kind of the boundary spring problem. So let's see what happens when you now move to x equal 2 meters. Well, you notice a couple things here. Zoom in a little bit here. First of all, if you compare the natural frequencies, you use the same K stiffness, you'll notice that first of all the first mode is still up here, kind of this rigid mode, but it looks even more rigid. So this is W1, and that's because the spring is now over here, right? The springs are going to be here and here, so they're not as far out on the beam. So that natural frequency actually looks in terms of frequency value, is very similar, but it's just not as curvy as before. This is omega 2, is this red mode shape here, W2, and then green and black are the third and the fourth one. Now, one thing you'll notice about omega 2 is that actually this number has gone down. And that's because, again, we're talking about same spring stiffness, but it's moved inward. So the effective stiffness on that rotation mode is lower. And here's the Bode diagram. Now you see a little more complicated stuff going on at kind of those first, here are basically omega 1 and omega 2 together. So there's two peaks and a zero, and again, if this was perfect, that zero would be cancel the second mode because we're still forcing it at the middle. Now this is what we were looking for with omega 3. We're looking for the zero here. And again, you have omega 4 out here is sort of a pole zero cancellation, as you'd expect. So this is the zero we're looking for. This means that if you excite this nodal beam at that frequency, you get almost no transmitted load to the ground. Okay. So that's kind of neat. All right, I did one last example where you really move the spring in close. The only thing that's kind of different here is that you see that because of the colors, now we actually have that omega 1 or W1 is actually that, and W2 is this. So again, the frequency of that kind of translational mode really hasn't changed very much. The difference is that the frequency associated with that rotation mode has gone down quite a bit, and now they flipped positions. But you still have a zero here in that third mode, which is what you're looking for. It's on a little different. It's on a different side. So again, we really shouldn't even see this guy at all in the response. It should be a perfect pole zero cancellation, but due to the discretization, it's not perfect. Okay, well, there you have it. 4 examples of using the finite element method. Hopefully that'll give you enough information to be able to complete the homework by Friday. So, see you on Wednesday.